Okay, so here's problem 1, chapter 10. And yeah, there are a couple of problems in there that probably do need some explanation, which you never got around to in class. So it says we have a copper wire with a length of 11 meters and a cross-sectional area of 2.4 times 10 to the minus 5 meters squared per second. And is stretched taut between two poles under tension of 75 newtons. What is the tension in the wire when the temperature falls by 10 degrees C? So this actually goes back to using some of the information in our chapter 10. So let us look at this thing. So you've got this copper wire that's stretched between two poles. Okay, so the length is equal to 10 meters. And the area, cross-sectional area, is 2.40 times 10 to the minus 5 meters squared. And the tension, which is a force, is equal to 75 newtons. Okay. So what you can do is you can figure out, this is using the relationship that says stress is equal to the modulus of elasticity times strain. And so what we can do is we can figure out how much strain there is. It's like our initial delta L. So remember, stress is force per unit area, and E is a property of the material. And strain is the change in length divided by the original length before it was stretched. So what we can do here is you can figure out, and really this 10 meters relative to the length, we could almost say L0 is 10 meters just to, I mean, it's really, this is really L0 plus delta L. But we can, so I'm just going to say L is equal to L0 plus delta L. We'll do it exactly right here. So we're going to do that. This is just the temperature, the original temperature, whatever that is. So we have a force, we have an area, we know that L is 10 meters. So what we can do is we can solve for L0. L0 is going to be equal to L minus delta L. So we could put that up here. So delta L over L minus delta L. What we're going to do is solve for delta L. Basically, how much do we need to stretch it to cause the initial conditions? And, well, actually, the difference between L and delta L, L0 is so small, it just makes the problem easier. So I'm gonna use L here instead of L0. It's not going to cause that much of a difference in our calculation. So you can solve for delta L. We just need E for copper. So if I go to the book, this is the book that you have, and we would look under Young's modulus in the table, in the index, because I don't know exactly what page it's on. So let's see if there's a thing that says Young's modulus. X, Y, Z. Okay, it's not under Young's, so it's probably under elastic modulus. So we'll look under elastic modulus. There we go, 347. Or there Young's modulus under elastic modulus, so it's 348. So we'd go to page 348. And actually it's on 349. Approximate elastic modulus for copper is 11 times 10 to the 10th pascals. So E is equal to 11 times 10 to the 10th. So now let's solve for delta L. So delta L is force per unit area. So what I'm going to do is I'm just going to divide by this, multiply that by that. So I'm going to multiply by L, divide by E, and that should give me the number I'm looking for. So my force, I had 75 newtons was the tension. I divide by the area, which is 2.4 times 10 to the minus fifth. 2.4 times 10 to the minus fifth meters squared. I multiply by the length, which was 10 meters, I think. 10 meters. And I would divide by 11 times 10 to the 10th. The units are pascals, which are pascals and newtons per meter squared. And if we look at the units, newtons cancel out with newtons. I've got newtons per meter squared here. So this meter squared cancels that out, and I just landed with meters, which is what I'm looking for. Delta L should be meters, and it should be pretty small. 75 times 10 divided by 2.4 e to the minus 5 divided by 11 e to the 10th. And so I get delta L is 2.84 times 10 to the minus 4 meters. So you see it's relative to L0 and L are pretty darn close to each other in our case. So for the accuracy we're looking for. So that's the amount of how much it has to stretch to get the initial tension. Now, it says what is the tension in the wire when it falls by 10C? So what's going to happen is that the wire is going to want to contract. It's want to get shorter, but it's going to be restrained. So it's going to hold the length. So what we do is we calculate the change in length due to temperature change. And we're going to add that to the change in length originally in the tension of the wire. So this is a delta T with respect to temperature. And we know that is going to be alpha times delta T times L, the original length, or delta T over L is alpha times delta T. So the temperature change doesn't matter. It's saying it's temperature change in Kelvin, and C is the same. So we look for linear coefficient of thermal expansion. Linear. So let me just say, let's look into thermal. Thermal expansion, linear. Okay, this is on in the index. Thermal expansion, linear, 551. So we go to page 551 to both. Oh, actually, if you go to 552, you'll see coefficients of linear expansion. Copper, 1.7 times 10 to the minus 5. So alpha is equal to 1.7 times 10 to the minus 5, and the units are inverse C. Okay, then you multiply by delta T, which is 10 degrees C. And it's actually negative 10 degrees C, so because it's going to get shorter. And we multiply by the length, which is 10 meters. So this is the additional amount that the wire wants to contract. So we take 1.7 times 10 to the minus fifth times negative 10 times 10 meters, and we get delta L temperature is 1.7 times 10 to the minus 3 meters. Yep. Okay, so you can see that on the order it's almost 10 times the change in length just due to the original tension. So we're going to add those together. So our total delta L, let's say delta L total now, that we use in the calculations is 2.84 times 10 to the minus 4 meters plus 1.7 times 10 to the minus 3 meters. And you do that, and you're going to get 2.84 e to the minus 4 plus 1.7 e to the minus 3, and I get the total delta L as 0.0020 meters. Okay, I'm just going to pause for a second. Okay, so I was just checking to make sure I was doing everything correctly, which I am. Okay, so now we go back and we use this relationship here, but we solve for the force, because what they're asking for here is what is the tension at the lower temperature. So if we solve for force, force is going to be equal to delta L divided by L times E divided by, E times area. Okay, so force, let's make sure we did this right. Force is delta L divided by L times A. Okay, and if we should get the right units when we do this. So we're going to use the total length, and we're going to divide by the 10 meters for the total. For the length, modulus was 11 times 10 to the 10th newtons per meter squared times the area, which isn't changing. The cross-section area is 2.4 times 10 to the minus 5 meters squared. And you see these meters cancel out. These meters cancel out. You just end up with newtons, which is what we're looking for. So 0.002 divided by 10 divided by 11, times 11 e to the 10th times 2.4 e to the minus 5. And I get that the force, the tension is 528 newtons compared to the original 728. And I'm just going to check my answer. Yeah, okay. So I probably can only use two significant figures because of the way I did the problem. So I get 530 newtons. So let's explain what we just did. So we had a copper wire that it was initially 10 meters in length stretched with a cross-sectional area such with a tension. So I used this relationship to find out what the delta L would be from, and I assumed that delta L was much smaller than L, so that I could, instead of using L0 here, the initial length, I could use the stretch length. So I found a increase in length associated with the tension of 75 newtons. Then, so I'm stretching that. So now I'm cooling it down so it wants to contract, so I have to pull harder to keep it from getting shorter. And I find the length that it would normally contract if it isn't restrained, to be 1.7 times 10 minus 3 meters. So the total amount this thing is stretched based compared to its initial unstretched condition is you have to stretch it 2.84 times 10 to the minus 4. On the original condition, you have to stretch it another 1.7 times 10 to the minus 3 meters to make it so that it's 10 meters after both things have happened. And then you use the relationship between stress and strain and the Young's modulus to back out the higher tension that results from the cooling down. Okay, we're on problem number 2, which should look very familiar if you've taken the test already, because I kind of based it on this problem, so it's pretty simple. So you have this pipeline, 1,300 kilometers long, and it's subjected to a temperature change from negative 73 degrees C to plus 35 degrees C. How much does a steel pipeline expand to due to the temperature difference? So again, what we have, the relationship we have is that the change in length divided by the original length is equal to this coefficient of thermolinear expansion times delta T. Again, it can be either C or Kelvin. So you have to find out what alpha for steel is. So if we go to page 552 in our book again, we just used it, and we look at steel, it says 1.2 times 10 to the minus 5. So alpha for steel is 1.2 times 10 to the minus 5, and the units are 1 over degrees C. So when you multiply it by C, you get no units, and delta L over L0 is no units. And actually, what we're trying to calculate here is delta L. So we're gonna multiply both sides to find the change in length. So you get alpha times delta T times L0. So pretty simple. Plug in the numbers. Alpha 1.2 times 10 to the minus 5, 1 over degrees C times delta T, which is going to be equal to 35 degrees C minus a negative 73 degrees C. And then you multiply by the initial length, which is 1,300 times 10 to the third, because it's kilometers, 10 to the third meters. So 1,300 kilometers is 1,300 times 10 to the minus 4 meters. And plug that in. So it's 1.2 e to the minus 5 times 35 minus a minus, I add 73, times 1,300 e to the third power, and I get 1,680 meters. So how do you do this? Well, you have to put in expansion joints. You wouldn't want to put them all in one location. You'd have expansion joints every so many meters or so many kilometers. If you put one every kilometer, you'd have to have an expansion joint of about a meter. For each kilometer, you'd have an expansion joint of a meter. So, you have to decide how you want to. Okay, so problem 3 is very similar to problem 1. So let's just read it. On the day when the temperature is 20 degrees C, a concrete walk is poured in such a way that its ends are unable to move. So it means it's restrained, but it's not under stress at that point. What is the stress in the cement when its temperature is 50 degrees C on a hot sunny day? Does the concrete fracture? So in this case, what we can do is we can, again, look at the change in length of the concrete. It's going to, due to the temperature change, is alpha times delta T times the original length. So the original length is, well, actually, I don't tell you what that is, but that's okay. So we're actually going to calculate delta L over L 0. And that's going to be equal to alpha for concrete, which is, well, let me just write out the equation. So it's just delta T times alpha times delta T. So alpha is, okay, so we're going to have to find what is alpha for concrete. Okay. And I don't see it in the new book, so I'm going to get the old book, if I can find my old book. Oh, there it is. So let me look at the old book. So it's chapter 10 in the old book. Average coefficients of expansion, concrete. Well, 12 times 10 to the minus 6. Well, times 10 to the minus 6. The units are 1 over degree C times the temperature change, which is 30 degrees C, and it's going to expand, or it wants to expand, but it can't expand because it's restrained. So as a consequence, it's going to be put under compression. So we get 12 e to the minus 6 times 30. And so the change in length divided by L0 is 3.6 times 10 to the minus 4 meters per meter in this case. So now we go to the other expression we were using, was the stress is equal to E divided by times epsilon. But epsilon is this thing right here. So we can calculate the stress in the concrete by taking Young's modulus, which is 7 times 10 to the 9th newtons per meter squared, multiplied by epsilon, which is delta L over L 0, 3.4 times 10 to the minus 4 meters per meter. And so this is stress the same as the units for Young's modulus. So 7 times 10 to the 9th times 3.6 e to the minus 4. And I get 2.5 times 10 to the 6 newtons per meter squared. Is that right? 1, 2, 3, 4, 5, 6. Now the compressive strength is 2 times 10 to the 7th. So because this is less than that, we should be okay. If this were greater than that, and I'm just making sure, we just check the answer here. Yeah, okay, so that's good. So this is the correct answer. So the answer to the first question, what is the stress? The stress is 2.5 times 10 to the 6 newtons per meter squared, or pascals. And because the stress is less than the compressive strength, then we say it doesn't fracture. It's not that close. It's almost off by a factor of 10. So we should feel pretty good about that. Okay, problem number 4. Now for some ideal gas calculations. So it says an ideal gas occupies a volume of 1 cubic centimeter at 20 degrees C and atmospheric pressure. So let's write these down. So we have a volume, we'll say B, V1 equals 1 times 1 cubic centimeter. So what is that in terms of cubic meters? Well, you've got 100 centimeters per meter. So what you're going to do is you're going to take this and we're going to multiply. We're going to divide by 100 centimeters per 1 meter cubed. So we're going to divide by 100 cubed. So 1 divided by 100 to the third power. The volume V1 is equal to 1.0 times 10 to the minus 6th meters cubed. Actually, did I cube it? Yeah. Meters cubed. Okay, so that's V1. T1 is 20 degrees C, but we don't use C. We add 273 to it to get absolute temperature. So you get 293 Kelvin. And the pressure is atmospheric pressure, which is 101 pascals, 101 kilopascals. So that's 101,000 pascals, units per meter squared. Determine the number of molecules in the gas container. So, we have PV is equal to nRT, where N is the number of moles. So what we're going to do is do it first. We're going to calculate the number of moles. So that's PV over RT. P1, V1 over RT1. As long as these are the right units, we're in good shape. So we have 101,000 pascals, units per meter squared. The volume is 1.0 times 10 to the minus 6 meters cubed. R is 8.314, and the units are whatever they are. You can look them up in the book. And the temperature is 293 Kelvin. And that's going to give the number of moles. So 101 times 1 e to the minus 6th divided by 8.314 divided by 293, and the number of moles is 4.1 times 10 to the minus 5th moles. Okay, then we have that the number of molecules just equals the number of moles times Avogadro's number. So where's Avogadro's number? If you don't remember it from chemistry, which I don't, because I don't use it that often. So I'm just going to look in the back of the book. Here we go. So it's in the back leaf, back of the back cover. Avogadro's number is 6.02 times 10 to the 23rd. 6.02 times 10 to the 23rd molecules per mole. And so and I get 2.5 times 10 to the 19th molecules. Okay, so we're going to check my answer before we move on. 2.5 times 10 to the 19th. Okay, that's good. Now the units are joules per mole Kelvin. So let's just fix that. Joules per mole Kelvin. Okay, so part B asks if the pressure of the volume is reduced to this while maintaining temperature, while temperature remains constant, how many moles of the gas remain in the container? So it's just a matter of doing the same thing, but reducing the pressure to a very small value. So we can just do the same thing. Number of moles, pressure is 1 times 10 to the minus 11. pascals, which are newtons per meter squared, times the volume, which is 1.0 times 10 to the minus 6 meters cubed, divided by R, which is 8.314 joules per mole Kelvin, times 293, because it said constant temperature. And let's plug the numbers in. 1 e to the minus 11 times 1 e to the minus 6 divided by 8.314 divided by 293. And I get 4.1 times 10 to the minus 21 moles. And therefore, number of molecules is equal to 4.1 times 10 to the minus 21 moles times 6.02 times 10 to the 23rd molecules per mole. And we get about 2,400 molecules. So there's a few molecules in there, there's not a whole lot. Let me double check my answer. I think I got that right. Okay, that's it. Okay. So our last problem is this one. A weather balloon is designed to expand to a maximum radius of 20 meters at its working altitude, where the air pressure is 0.030 atmospheres and the temperature is 200 K. If the balloon is first filled at atmospheric pressure and 300 K, what is this radius liftoff? So this is one of those cases where N is constant. There's no moles leaking in or being put in. So we can use the form of the ideal gas law that just involves pressure, temperature, and volume. And in this, because of that, as long as we're consistent with the units, we don't have to convert stuff. So you can see we've got atmospheres and atmospheric pressure, which is 1 atmosphere. So let's just go through and we'll say 1 is atmospheric pressure and 2 is altitude. So P2 is 0.030 atmospheres. We don't know V2. And V2, we're going to assume that this thing is a sphere. So, or do we need to worry about that? Yeah, this is radius. So V2 is going to be 4/3 pi R2 cubed. Because that's what we're trying to find. We're trying to find, actually we know what R2 is actually, don't we? But we'll leave it in there for right now as radius. We'll fix it later. Okay, the temperature at altitude is 200 K. We don't have to change that because it's already in Kelvin. P1 is 1 atmosphere because it's atmospheric pressure. V1 is 4/3 pi R1 cubed. And T1 is 300 Kelvin. So we know everything except V1, which will allow us to do R1. So let's first substitute the equation for volume. So we get 4/3 pi R1 cubed. That's V1. T1 And then you get P2 times 4/3 pi R2 cubed over T2. You can see these are going to cancel out, and these cancel out. So we're going to solve for R1 cubed. So there's R1 cubed. So we're going to multiply by T1 and divide by T1. And then I'm going to group the pressures together. So I've got P2 in the numerator, so P1 has to be in the denominator. I've got T2 in the numerator, so T1 has to be in the numerator. I've got R2 cubed over, I'm solving for R1 cubed, so there's nothing there. It's just, so it looks like I can, let's solve for R1 cubed, and then we take the cube root. So P2 is 0.03 atmospheres. P1 was 1 atmosphere. T1 was 300 Kelvin. T2 is 200 Kelvin. R2 was 20 meters. And that's cubed, and that'll give you R1 cubed. So let's see, we got 20 cubed times 300 divided by 200 times 0.03 divided by 1. So I get R1 cubed is 360, therefore R1 is equal to the cube root of 360, which is the same as raising it to the 1/3 power. And I get 7.1 meters. That makes sense because, weather balloons get larger as you go higher in altitude. So you'd expect the initial radius to be smaller. And let's just check the answer. And that's correct.